So here's what we can do as people are settling down. I know that Shantanu had a question for you, Cole. So Shantanu, can you ask your question now?
Actually, it was already answered over
Oh,
chat.
what? Oh,
Okay,
it's been addressed on chat. Okay,
yeah.
great. There were still some pending questions. Let me see if I can recall. I think Bruce, you had a question for Aditya. Sukant had a question for Varun. Sanjit had a question for Aditya. So yes, I believe I've got everybody, but if I have not, please let me know. So perhaps we could, start with Bruce. Yeah.
So you've already heard my question just over tea.
Yeah.
But maybe I'll repeat it for everybody. I was asking whether in the analysis of the LVK data to try and constrain the distribution of masses, the properties of the observed population of binary black hole mergers, whether only the events that have been reported as detected, I guess that means more than false alarm rate of less than once per year, were used, or whether also the sub-threshold events were used, because the sub-threshold events should have a lot of additional information in them. And maybe you answer that.
Yeah, so the short answer to the question is there are methods that are developed to sort of self-consistently include all triggers that we get from the detectors and fold it into population modeling. So we in the flagship LIGO-Virgo Kagra collaboration papers, we do not do that. I know Shashwat has worked on methods to include subthreshold triggers. I know people in the IACS group have done this. My understanding is that once you go below of the 1 per year limit, your P astro also drops quite fast. And so at a point when you keep adding more and more triggers, and you'd have something like rho to the 5. I mean, if you reduce your threshold by a factor of 2, you would have like factor of 2 to the 4 more triggers. And at some point, like the P astro, like the astrophysical probability of the trigger drops so low that you really don't get much more information. And of course, the parameters become worse measured and stuff like that as well.
Learn about any one system, then you don't get any reliable information out. That might well be noise. But here you're trying to only find a few parameters. You're trying to find the height of the curve, a couple of slope values, just a few numbers. And so then incorporating this sub-threshold information, there should be quite a significant amount of information there, even though any individual event is sort of unreliable.
I mean, I agree with you in principle.
This is just on general principles.
Yeah.
So I have a follow-up on this. Stacking helps in some cases, but not in all. So for example, we did a similar analysis to see if there's any gamma ray emission from black hole mergers, because 150914 came with a GBM candidate. And what we found there was that the 2 closest events that have been detected in all the 4 runs so far, up to 03, completely dominate the statistics over everything else added together. So sometimes you really do end up adding just noise. But broadly, yes, stacking analysis I'm strongly in favor of.
Yeah, I mean, I would like to advertise one paper which I don't think got a lot of attention. Reed Essick put out a paper called "When to Sweat the Small Stuff," and his when to sweat the small stuff. Essentially, when do you reduce your threshold? And he was looking at it mostly from the perspective of next generation detectors as to how low should you go. I mean, is it okay to just put a threshold of 20 and you'd still have like 10,000 events, or should you even, and I mean, as expected, the answer is that it depends on how much information you add per event multiplied by root n, something like that, right? The number of events that you gain. So yeah, I'd recommend people also read that paper, because I really had a lot of fun reading that paper as well.
This question also, I got a chance to discuss with Varun during the coffee break, but it may be of broader interest. It's about this elusive spectral information about the early emission from a kilonova, right? And it's not limited to the 250818 case you're discussing, which is interesting in its own right. But rather, in the last 8 years since GW 170817, how well have we prepared to be able to actually see that emission simply because it can resolve some of the competing kilonova models, right?
So I can explain the workflow that happens after these triggers. So depending on how distant the event is, we first have to take a call on what are our odds of seeing something at all, right? If there's an event at 600 megaparsecs, you put 17 there, you would miss it anyway. So based on if you are going up to 200, maybe 300 megaparsecs, then people start following up. A bunch of wide field telescopes then start tiling the whole area, and in a random field of view, if you image 100 square degrees of the sky, you'll find a bunch of transients every single day. Okay, so you really need to have continuous coverage. You need to be going in. We find hundreds of false positives, and then we have to, which are legitimate new objects in the sky, but we know they are not related to this because of their characteristics. We, as in the global astronomical community, does not have the resources to take spectra of all of these. So the first round of vetting has to be done photometrically. And by the time you rule out most of these candidates, you come down to a handful, say order 10, then you start going to spectra. Unfortunately, by then they've faded. So you need even larger telescopes to follow them up. And then you have beasts like this one, which change their behavior, saying, aha, fooled you. And then you really can't do much about them because most other candidates, people will have stopped following up. Okay, the other candidates that looked CV-like in the beginning, if they did a turnaround, I don't know, because we did not follow those up. This looked kilonova-like, so we started following up. After it changed its behavior, other groups dropped off. We stubbornly continued following it up because we had other ways to explain this behavior. And finally, we said, look, we are going to just put this to the rest, and continued following up. But the problem is a problem of sheer numbers. As long as localizations remain thousands of square degrees, even if all telescopes stop doing everything else, it still remains an intractable problem.
Which is the following. It is slightly after 5 o'clock on the 28th of October, 2025. Now, there are people in this room like Bala, Iyer, or Sumanta who've worked for many years for LIGO India. LIGO India will add a large baseline to the LIGO instruments, and the single biggest effect that's going to have is it's going to increase the pointing accuracy by an order of magnitude, which is going to help a lot in these follow-ups. And so people should be aware that 10 minutes ago, the bidding for the construction.
It has got extended by a few days.
Oh no, oh. We have to celebrate, all right. I'm completely deflated.
So we are actually doing, so Sanjit and Sanjit students, and I'm helping them out, are doing a study about this, saying that how will LIGO India change the EM follow-up game in the case of both above threshold as well as sub-threshold events, by the way. So there's, and Sanjit claims it will be like orders of magnitude changes. So we'll wait until.
Well, orders of magnitude.
In rates.
It's a, see that, no, it is not bad. It is like maybe 10-20%. But when you consider the cost of each of the detector, 10% is a lot of money. And also, you know, this is not concluded, so let us not comment on that right now, because there are.
That's why I can claim orders of magnitude, right?
I can ask my question. So my question, I got partial answer to with discussing with Aditya during the break, but it is not very convincing. It is about the selection bias. So when you get a population of binaries and you are inferring the actual inherent population in the universe, I'm not very sure that you can actually do that confidently. Okay. What you can do rather is that I have this specific model, and what is the chance that this model is ruled out? The reason is that there are several variables in the, you know, on which you are marginalizing. But in the universe, there is only one specific model. Marginalization does not take care of that. I mean, suppose there is a, like T2, let's say you take some delay distribution. Let's say it's a secret distribution in the universe, right? But since you don't know, you are marginalizing with a proper distribution, does not mean that the effect is completely accounted for. there is a fixed distribution, that's what it is. So probably you can only say power law is ruled out or not and things like that. But you cannot probably say, here is the real distribution, like projected distribution back in the universe.
I mean, so I don't know if this is what you're getting at, but yes, I mean, like if you have some model which is underlying and then you didn't know it, of course, I mean, that's the point of inference, and you make, say, a wrong choice for your candidate model that you're trying to fit to the data. I mean, of course, you'll have issues with model misspecification, but that's not the fault of GW data. I mean, like if you had, I mean, in principle, if you have infinite number of events and you had modeling methods that could take into account this, say, multidimensional population of binary black holes in the universe, you can actually infer it precisely because you understand your selection effects very, very well. So
Probably you can, but even then, in a simple universe, like when you are just looking at stars, etc., maybe it's possible. But when you have binaries where you don't know the time delay distribution, then the formation channels, etc., I don't know really if it is possible. There's so much going on in the background.
I mean, so I can always solve the forward problem, right? I mean, like say I had an intrinsic population model. And so, I mean, my likelihood is just allowing me to invert that forward problem into a backward problem. So in principle.
The part I'm not very sure about. Forward problem, I agree. Whether there is a mass gap or not, probably you can rule it out with certain confidence. But
yes,
whether you go back in the, whether you can invert it, that part I'm not very sure about. Invert, like where you can, you were saying that this is the distribution of the binaries in the equation. That I'm pretty sure.
I mean, so I can definitely tell you that I can write down a likelihood for that process, right? And I mean, the whole point of Bayesian inference is to solve these inverse problems. So if I can write the forward model, then I can also do the backward problem.
Of models, right? So
yeah.
Even if the uncertainty is like, maybe if n observation is infinite, maybe at that point of time it will become very sensitive. But what you're saying, I agree with.
I mean, but that's the case with everything, right? I mean, binary black holes.
It's about discarding the models, right? You cannot say, right, that this is the model. It's about, okay, this is less favorable or more.
I mean, but that's exactly what we're doing with waveform models as well, right? Like, I mean, we can't say that some waveform model, NR surrogate 7DQ4, is the underlying model. We have one model and we're saying how good it is fit against the data. So,
okay.
So related to this, I will just add another googly on that. Okay. So basically, what your data you were looking at is the mass distribution of binary black holes, let's say. Okay. And then you have some forward model, some backward model. We can debate about this power law, not that power law, or whatever complexity you can put in. In the end, you find there is a gap or not a gap, okay? And then you are trying to infer something that is actually a jump of a logical step. You are saying that black holes, single black holes, cannot be produced at that mass range. That is a big jump. In principle, what can happen is single black holes very happily can populate this mass, but those black holes form through some binary process that do not end up in binaries that would merge within a Hubble time and be detected. So, exactly. So one should keep these things in mind.
And then we'll move on to a broader discussion.
I'm puzzled by the term selection bias here. So for example, suppose radio astronomers are trying to infer what the population of millisecond pulsars is in our galaxy. This is difficult to do because, for example, parts of the galaxy are less visible than others. They're obscured by dust and has high dispersion measure. And so it's quite difficult to go from the data, the observed population, to conclude what's the population in the Milky Way. And that's selection bias. You know, what fraction of systems do you actually see? But LIGO does not have that problem. The universe is completely transparent to gravitational waves. If you tell me the parameters of a source and how far away it is, I can tell you what the signal to noise will be in LIGO within ±1. And so it seems to me that we can make inferences about the population with no selection bias whatsoever. So why are people talking about selection bias?
So the only way I'm trying to refer to selection bias is just the fact that, like, if you have the fact that you don't observe binary neutron stars to whatever 1000 megaparsec. I mean, and the fact that you can't observe, you observe more binary black holes than binary neutron stars is a selection bias in your observed population. However, I completely agree with you that you can correct for it precisely. And that I am completely agreement about. Sure. Yeah. I mean, if that's your definition of bias, then
I
Well, I agree. There is no,
Yeah.
just a terminology different. Let's move on to the next topic.
Yeah, actually what I wanted to do is there was a student online who wanted to ask her question during one of the talks. I think it was Sanjeev student. What's her name? Yogita, if you're there, can you ask your question to the panel?
Hello, everyone. Hello.
We
Am
can
I
hear you. Yes, yes. Please go ahead.
Okay, my question was related to NSBH mergers EM counterpart. Like I was going through its existing models and all. So I just wanted to know what is the expectance level of these models in the community and how reliable these models, radiative transfer code models for producing the light curve are, and the analytical formulas to get the ejected mass present in the literature.
Okay, so I can answer this in two parts. First is that if you are looking at something like a kilonova, that is something that is pretty much at that stage decoupled from the central engine. So it's only a question of how much ejecta was there, and was it in the form of high velocity winds or low velocity material that would form a disk. So if you have a model which says that a neutron star black hole merger gave you, say it was not a high mass ratio object, and the merger gave you 0.02 solar masses of material outside, then that will look identical to a kilonova created by a BNS merger which did the same thing. Now, so this is part one. The other part comes to how is this mass being left out there? And that has now got to do with, I think, GRMHD simulations essentially of what's happening with the neutron star as it falls into the black hole. Whether it will launch a jet, how much ejecta mass will be there is all, if I understand correctly, and I think Rahul can probably correct me if I'm wrong, is based currently on a small number of numerical simulations which are then being used to extrapolate. So the overall expectation at this point is that we should be able to see kilonovae. And as far as the gamma ray counterpart, which would come from the jet that is being launched, there are huge uncertainties. There are some models which say that if you have a low mass ratio object, then you could actually create much brighter gamma ray emission. And there are others which say that you won't see anything. And until we have a joint observed confirmation or a few, it will be hard to actually figure out which is which.
Okay.
Sorry.
So Rahul can.
Yeah, good.
I wanted to add like very small. So actually, we have a paper coming out, Ish and one of a student at IIT Bombay. So the first thing is that when neutron star gets disrupted, they form heavy elements and then they decay radioactively, and that powers the light curve. And same thing happens in BNS, as Varun said. There is no difference. The only difference is that depending upon the parameters, masses of the systems, like masses of the neutron star or black hole, what is the distribution of the ejecta mass, velocity, and opacity? And opacity is can be so electron fraction of the ejecta is proxy for the opacity. So this distribution can produce distribution of light curves in different space. So for example, you have some band light curve, and that has that peaks a bit early for NSBH compared to BNS. And these patterns we are finding. We are finding some patterns. So given few observations of NSPH and BN, and not we can't distinguish. We'll just have few observations of kilonovae. Let's tens of, and then we can say that these are coming from NSPH or other coming from BNS. And regarding numerical simulation, I think I just pointed out earlier today that we have very few simulations, and we have to do more simulation. One other thing is the mass ratio thing. For the BNS, almost all of the system will produce kilonovae except the prompt collapse. But Kenta can argue against that actually. But for NSPH, if you have mass ratio more than 4, then they just black hole swallows the neutron star as a whole, so there is no disruption. So again, there is a very narrow mass range in which you will see,
Okay, I think I'd like to move on now to the other panelists who haven't yet had a chance to share their thoughts, and then there are a bunch of questions that they've put down as well. So we can start with Reshmi. I think you had a slide that you wanted to go over.
So for the discussion, I had in mind a couple of questions that are not covered in the session in general. So one of the thought I had been having in mind is the question of a large number of binary neutron star mergers getting detected during the A-sharp time, or even CT or Cosmic Explorer or Einstein telescope time. So there is very likely you are going to get some events with a low inclination angle, which means if there is a jet that is produced, it's likely that jet could be at least slightly more aligned towards the observer, then the story totally changes. If that happens, it's much easier to get an electromagnetic signal from the relativistic outflow from the jet in the form of probably gamma ray burst as we know them, or maybe some other crazy transient in the high energy regime. So I was just trying to do some calculation of it. So I was just using the BNS rate from the GWTC4 and just using the Schultz distribution, trying to just calculate, and I kind of get these numbers for an iota less than inclination angle less than 10 degree. I get something like 0.05 to 1.6, but this assumes that every BNS merger has a jet. That's under that assumption. And you have an instrument in the gamma ray or X-ray in the high energy instrument that can see the entire sky, that does not miss it. In this favorable scenario, you get these sort of numbers. I put in a number of 10 degree because that sort of have opening angle of a jet. Or in fact, a 20 degree may be also not a bad idea. It also depends on what sort of mass and velocity distribution the jet has. If GW17 or 17 is something that we can kind of extrapolate, then probably even a 20 degree will be a good idea. So my hope is that in future, even when kilonovae are not, at least not probably detectable, or not, the spectra are not easily taken, I believe that GRBs or other similar high energy transients have a better role to play. So the sort of questions we can ask is whether do all BNS, I mean, we still don't know the answer, whether all BNS produce jets, if so, what sort of jets, and what kind of transients are going to come out of it. Is it going to be a classical GRB or something else? And just now, the question what was asked earlier, we can also get to some idea about NSBH mergers. I didn't put in those numbers all that much because NSBH mergers, there are, as Rahul and Varun said, there are lots of other parameters like the mass ratio and the spin of the black hole. And the other point I wanted to mention is about the life after merger. So there have been a lot of searches for quasi-periodic oscillations in gamma ray signals. So this paper, which came out in 2023, if Cole is there, he's one of the authors. They have found a kilohertz QPO in 2 gamma ray burst in 1993. And they try to argue that this is a central engine or it's a highly spinning neutron star that's producing it before it collapsed to become a black hole. There are also one paper, which is again recent, and I don't know how much, I am not qualified to comment about it. They found a very low frequency QPO. They're trying to claim that it is a precessing jet. This is found in the afterglow phase. There are also questions about magnetar-powered kilonovae, which Rahul may be the right kind of person to answer. And I'll just quickly go through the next slide. There are also, this is something I added yesterday and today, because after coming here, I got interested about the decihertz multi-messenger astronomy. So one of the questions which I think yesterday there was some level of discussion about it in the double white-dwarf merger and supernova 1A. So I was just talking to Jan in the afternoon. So in the 10 megaparsec volume, that is the detectable range, you don't normally have very large number of supernovae. Their rates are like 2.5 into 10⁻⁵ per megaparsec cube per year. So I'm just hoping that there could be some level of multi-messenger astronomy that could be done with DESIGO and similar instruments. I also wanted to just touch upon BNS pre-merger emission, which is thought to be responsible for FRBs in some model, where the weakly magnetized neutron star before merger goes through the magnetized neutron star disk and produces some emission, which is coherent radio emission. There are also other forms of coherent radio emission predicted. There's a lot of them in this paper. There are lots of searches along with short GRBs for detecting coherent radio emission, like MWA kind of arrays and similar fast radio burst sort of instruments. So to detect fast radio bursts, etc. Nothing much has come out of it. I'll probably skip the last point. So I just want, this is what I basically wanted to cover.
Okay. So as you go back, I just wanted to check with Otto and Kuntal. Did you have anything you wanted to say to start off the discussion? So I see that the first question in bold is Otto's question. Did you perhaps want to elaborate on that or have any opening comments?
Yeah, definitely. Thanks a lot, Shashwat. And apologies that I was not able to make it in person, regretfully. So maybe I can elaborate a little bit, because the question is really about sort of three things, and I'll try to maybe go through them one by one. So I've written there about sort of unique advantages, growing avenues, and challenges in combining different messengers. And I noted down sort of while listening to some of the really nice talks from the speakers, sort of a couple of things in relation to these three points. In terms of sort of these growing avenues, what I was really referring to is things that are sort of at the borders of what people kind of discuss about. So one of the things that kind of fits in this growing avenue category is what Aditya mentioned about these eccentric waveforms. So one thing that would be from my side really interesting to understand is how do, let's say, some of these new avenues that we think are going to become accessible in the future, for example, eccentricity, how will that impact some of the science cases that we've been discussing? So including these formation channels, and eccentricity is one example. I would put maybe lensing as another example, and I'm sure that there's many others as well. So I think one thing that I would really like to hear about is sort of what are the things that we expect to change in the near future, and how does that impact some of these science? So I think Varun also mentioned the many upcoming detectors. I think it would be really interesting to hear how those will impact the, let's say, the multi-messenger science, for example. And the unique advantages, what I am sort of referring to in there is actually quite related to the selection criteria question. And so there was, I think, a question about these selection effects in gravitational waves. And it was sort of mentioned that, for example, the binary neutron stars that are seen in the LVK are not seen to very high redshift. But then I think with other instruments, I think there are sort of complementary ways to maybe indirectly observe a lot of these things. So I would be kind of curious to hear more about specifically the complementarity of some of these approaches. So let's say in relation to formation channel studies, have people thought about sort of combining more the electromagnetic data with gravitational waves? And then lastly, on the challenges, I think, of course, this is sort of related to all of these questions. I think especially what Varun mentioned about these EM searches, that they have sort of their own unique challenges. So that's something that I would love to hear more about. But it's a fairly broad question, and it sort of is really three questions in one.
Okay, maybe I could just check with Kuntal. Did you have anything you wanted to mention either about this or your question specifically? Oh, you did not there? All right. So I guess the next thing I could do is maybe just cover the two other questions in bold, and then after that we can just open the floor for discussions. Cole, did you want to perhaps elaborate on two of your questions which are written in bold?
Yes, thank you. So I think that I mentioned both of these very briefly in my talk, but I think that one of the things I'll exacerbate the first one. So the clarity on the formation of black hole binaries. Okay, sure. Starting my video. Hello. The exacerbation is the following. One of the challenges is that prior to the detection of these events, people would have imagined that certain specific types of binaries would point in one direction or another. For example, if you have clear eccentricity in a binary, this is easier to do by dynamical channels than it is by isolated binary formation. But one of the challenges now is that there are very few of these. And that means that since there are very few, you can imagine unusual pathways leading to an eccentric system, even in an isolated binary. For example, if a kick happened in the right direction. So I think that's part of the sharpening of the discussion there. And then in terms of the second one, the higher order tidal effects like oscillations. Here, of course, if we were really able to get a lot of different frequencies from oscillations, then we would have neutron star asteroseismology. And I've been interested for a while in the possibility of laying out exactly what we would learn. To repeat something I said in my talk, an F mode is largely dependent on the average density of the star, but G modes could actually tell us things about phase transitions as a function of density. So that's kind of what I had in mind.
Okay. So now let's open the floor for questions. Okay, yeah, please start. Yeah.
Hello, Cole. I have a question for Cole. So in your slides, you mentioned that no clear sign of deformability was seen in GW 1708-17. Now there are papers that try to constrain the tidal deformability parameter, and although the error bar is quite large, they are generally above zero, right? So are those results still in doubt, or is that not what you meant by not being confident about deformability?
So what I meant by that is that, as I understand it, not having done the analysis myself, if you look at the estimated tidal deformability, it also depends fairly strongly on your prior further rotation frequencies of the neutron stars, meaning that there's something maybe there, which is why you're pushed away from zero. But if you allow the stars to have spun fairly rapidly, faster than what we see in galactic double neutron star binaries, I think you can accommodate that without actually seeing tidal deformability. So I think that's the restriction. If we believe strongly that these neutron stars were rotating at hertz or less, then the tidal deformability evidence becomes a bit stronger.
I see. Thank you. And I had one comment regarding your second question, which is what we can learn from higher order tidal effects. So with the static love number, we can only say how the neutron star is when it is perturbed by very small frequency perturbations. So in some sense, we cannot learn what happens when the reactions, say, cannot maintain equilibrium when you perturb them. So in case there are any hidden physics that reveal themselves by when you push them out of equilibrium. For example, people say that when there are hyperons in the neutron star, you can create bulk viscosity. And that bulk viscosity is created, as far as I understand, because those reactions are unable to maintain equilibrium when you start to wobble the neutron star. So signatures of such quantities will be revealed, for example, through viscosity, which is going to contribute to dynamical tidal effects. So yeah, that's one thing. And the other thing, as you also mentioned, G modes, which can reveal to, which also depend on the chemical reactions inside the star, because they are really buoyancy modes. So you are asking what happens when I slightly perturb the star. And we have seen in a couple of papers that the behavior of the tidal response can be reasonably different when you are below the G mode and when you are above the G mode. So during in-spiral, we can also see a change in tidal parameters at the dominant G mode frequency.
I think that's an excellent point, and I believe it also points to the importance of continuing to improve the high frequency sensitivity of gravitational wave detectors. And in terms of viscosity as well, it should be mentioned that after the merger, if you have a hypermassive neutron star which is oscillating, then various contributors to viscosity, including neutrino transport, could be quite important.
Thank you.
Hi, so question for the panelists and everyone. Two comments on the way you want to take it. First one is on multi-messenger. So right now we look for an event which looks like a potential candidate. It's not a discovery. We look for an event which looks like neutron star binary, looks like neutron star binary black hole system, or so on. So but there's a lot of ignorance in our modeling. So possibly a discovery space will happen when we don't know what we are going to find out and we find something new. So what is do you think the way forward to go for a multi-messenger driven discovery space? This is not only for the panelists, but for all of us as well.
So
just to start some discussion on this.
So part of this is already being done, right? So the question is, how many unmodeled transients does the GW community send out? And the answer is embarrassingly small, right? We do treat them on par. So as far as follow-up is concerned, we do not apply a very different set of criteria for an unmodeled event. So if I get a CWB event, if it is a high mass tuned CWB event, for example, I'll ignore it because we know there won't be a counterpart. But if I get a generic CWB event, then whether I follow up or not, the criteria applied are pretty much the same that we would use for a BNS event. Once we start getting candidates from the EM side, then we will not apply as stringent filters. I don't expect the counterpart to be a BNS-like thing, but there just aren't enough triggers out there. And I think that is again where LIGO India will make a difference, because having more detectors online will allow you to really dig into the noise on that front. And that's going to matter quite a bit, in my opinion.
No, so this is driving from the slide which you have shown. How do we know we are not discovering something absolutely new? We have a gravitational wave something. We have an EM observation, but none of us are able to confidently say we have discoveries.
Okay, that is where I actually want to issue a call for arms. Okay, and that is there I think the GW community will have to lead, because you are far more coherent or monolithic, I would say, as compared to the EM community, where there are like 10 large groups which are competing for the same stuff. GW largely, with some caveats, is a more integrated community. Okay, so let me take 250818K as an example. Okay, the two analyses have been so far, and by default will continue to be completely unrelated to each other. Okay, but for instance, the fact that the candidate that we've found is at 400 megaparsecs should go into your searches, saying that we are no longer running a search that's blind over this, and that will improve your estimates, for instance, for the masses, right? Because your signal now has to be stronger to have the same strength from 400 instead of 300 megaparsecs. And while your median chirp mass might indicate something, that's just going to go up by 33%, right? And that changes a lot. Or if you look at what kind of EM emission do I expect, EOS is a hidden parameter that goes into all of this. EOS is deciding how much tidal deformability is there, how much, whether it is large enough to impact your waveform, I don't know, maybe it is. It might impact how much ejecta is created, that's going to impact how bright a EM counterpart I should expect. The inclination angle that we are able to constrain for this source is like with an error of 10 degrees or so, but that again should go into the GW calculations. And in the current way these things are set up, it won't.
No, but
Okay, and by itself, no, this is not just for this event, right? But by itself, this is how we have been working. I'm just using this particular event as an example, but this is how the two communities have been working. And I will again say this stems from the choice of LSC, not LVK, but the choice that LSC made to begin with, which is that astronomy is not part of what LIGO does, right? The job was outsourced to astronomers, saying we will release some information and we'll control how much information is released, and we'll write our papers and let them write their papers. Now we've done that for a decade. Now it's time to move on, right? There shouldn't be a we and a them, and we should figure out how to do these analysis together, because there's so much more that we will learn about it. And that is what needs to happen on all of these fronts for joint analysis. So the same extends to unmodeled searches, for example. The sheer number of transients that we find in optical and X-ray right now is so large that a meaningful blind inverse search is not going to be possible. But if we start looking at ways of how these unknown transients, so we apply filters on the astrophysics side, right? We know which are standard no way, and we know that we can rule them out, and all other M dwarf flares and all these contaminants. And then you could say, okay, now for each of these transients, and let there be a million of it doesn't matter, right? You now do a coherent search in that direction for excess power. That still might tell you something. But that requires more of these discussions where there are astronomers sitting and GW people sitting, and they're not married to their own surveys or their own analysis pipelines or something, and are willing to ask crazy questions, saying that given that we have godlike computing powers available today, how do we utilize them to find scientifically interesting things? And that is not happening. I would politely, I will say not enough of it, but practically I would say almost none of it is happening. And that is really where we need to step up, saying that there is probably interesting, scientifically interesting stuff already in our data, and we are just not looking for it. And it would be really sad if 10 years down the line, somebody runs an archival analysis and finds cool events from 2025, and we didn't find them because we never looked for them.
Good. I mean, I think I'll get back to this point as well, because I have another point to make, and I have others also to make.
I think he also wanted to.
He says something.
No, I mean, it was just a doubt. Like, why do you think the chirp mass would change? Because really, the only thing, only freedom that you have is inclination and this.
No, redshift.
I mean, but that's you. I mean, if it's at 400 megaparsec, it's practically very nearby.
Almost like 0.1. I mean,
Yeah, I mean, it's not
sure,
but
yeah.
maybe not by a small amount. Sure.
Yeah.
Okay.
But one more point is maybe again general comment regarding physics-driven inference from gravitational wave data you are seeing. Other is model independent search. So where do you think is kind of the balance will be? Like I can have 10 parameters to get an inference, or I can make a model independent search by Gaussian process or anything else. Where is the balance? Possibly will be going with 1,000 events. Again, a comment for the panelists and everyone. Over.
It's hard to answer. It depends on what you are really after, right? So, like if you know what the physics is, some formation channel, some particular source, and you know how they form, you know what to expect based on what you understand of the physics, then you should go from the physics side. And since your theory can predict something, you can then compare with whatever you are observing and so on. And sometimes you will succeed, sometimes you will not. on the other hand, if you find something that's just crazy, and you have exhausted what you know from you understand the physics, then sure, go ahead and do your parameter-free modeling and release the parameters, and maybe some other kind of physical model will show up. So the reason why I said these two in this particular order is because if you first do the second thing, then that rarely tells us anything that is usable in a physics sense. I mean, for example, any data you can feed a Gaussian, but then what does it, the mean and standard deviation mean?
So,
Sorry, just one quick comment. Yeah, so I think there's some belief in the community that the second way that you said is the more, I don't know, correct way to do things. I am agnostic to that. I personally think, so this is what I mentioned in my talk about robust features as well. I mean, especially, and I think this is also what Cole was mentioning in his talk, like, you know, if there is something that is only predicted by, say, one kind of formation channel, then we should definitely, you know, sort of pin onto that feature and look for that in the data. But I think, I don't think the second approach is completely useless as well, because you know, it might allow us to sort of characterize those features better, which might not have been predicted by formation channels at all so far.
I can give you astro examples from both sides of this, okay? In X-ray astronomy, the common adage is that if you torture data enough, it will confess to anything. Okay, so if you take time series data and you start looking for pulsations, and you can start saying that, oh, okay, maybe it was pulsating only in the third epoch and not the others, and so on. And we have seen, unfortunately, non-negligible number of papers where people have dug into noise and claimed a detection. Okay. Then on the other hand, when PTF started, the Palomar Transient Factory started a decade ago, they said that we are not looking for supernovae, we are looking for things that change in the sky. Okay, and they started finding all these new classes of transients, which are considered very important today. And then people from supernova surveys who were doing 1A cosmology did confess graciously that we had actually seen these kind of things, but because they were clearly not 1As, we threw them away. And we missed the opportunity to do all that interesting physics. So we have seen examples from both ways. And it really, you have to be careful about which way you are heading. You don't want to throw away interesting candidates, but you don't want to run after noise either.
I think Cole has a comment to make. Cole, please go ahead.
Yes, thank you. So first of all, I want to strongly endorse the point that if you torture the data enough, it'll confess. And I think that there's several components to this to help us out. One is that when it comes to gravitational waves, we're still in the process of obtaining large enough libraries of waveform templates to get reliable information. A good example is GW 231123, which has this very high mass and so on, but the different waveform models tell us different things about the exact values of the spin and mass ratio and whatnot. And that's important because if the waveforms can eventually converge, we're going to be able to get better info and then determine how exceptional it is. But then the other point I'd like to make is sociological. The idea, and it's happened over and over again, that people will make claims that don't stand up. For example, there were claims about echoes in some gravitational wave events. It's difficult, but if we can try to repeatedly hold ourselves to high standards of evidence, then this is going to do everybody a favor. Otherwise, there's noise from the community. And it's tough, but when we see something that looks really interesting, we have to ask ourselves multiple times, is it real? Are there reasons why this might not be the case? That's going to help the community move forward, and it will mean that when there is the claim of something spectacular, if it holds up, then everybody is happy. It is a challenge because it's also exciting to publish our own papers. So I don't know what to do about that except to just remind ourselves every now and then that not every bump is actually real.
So I had a question to Arun that about the GW alert. You are saying that it came somewhere from 400 megaparsec. It was like a BNS kind of signal, but in EM it is looking like supernova kind. So are we missing something that, or do we don't understand how the EM counterparts would look? And
okay,
we
so
have
this is something which I want to clarify again. Okay, in the interest of time and assuming that at least half of you had heard me talk about this a lot of times, I skipped some of the details there. If you give me a completely random 1000 square degree patch of the sky tonight, okay, and I start surveying it, I will find a few thousand transients within a week. Okay, let's have that number in mind. Rough, one transient per few square degrees per week, trivial. Okay, so now it improves thanks to a distance estimate. So within the localization volume instead of the localization area, we still found dozens of candidates, new things that legit astrophysical events that happened there. Okay, then we have to figure out where there means that part of the sky. We don't know distances to most of them. A lot of them turn out to be galactic things, CVs, flares, things like that. And then within that enclosed volume, you say, I found something new. That does not mean it is the same thing that you did. Because for example, if right now you simply know that there is someone speaking in the room, you don't know who is speaking, right? And because the sounds are coming from the speakers, you don't know if it is me speaking or him speaking or she is speaking, right? So you now have to start looking at characteristics of the voice. Do you know whose voice this is in order to place it? So we have found a transient that we could not rule out. We found a few dozen others which we could rule out, saying these are definitely unrelated. And this is what happens with every single GW event. This was also the process that we went through for 170817. It happened to be so bright that the thing was very unambiguous, right? So it's not that we don't know what kilonovae will look like. The point is that we have just discovered that we can make a classical GRB plus kilonova look exactly like a supernova. And that is where the problem is. And then there are hints from spectra that it is a supernova in 1 out of 10 spectra, and the other 9 don't look like a supernova. But that one, we don't know how to create that from a kilonova. Right? And as far as this event is considered, there is no chance to get any more data. It's too close to the sun. We barely got one last photometric point 2 days ago, which we haven't even been able to reduce yet because there are a lot of issues in the data. And it will not be visible again until February, by when that thing is going to be gone. Right? So these are the details of astronomy that need to be factored in. And this is again going back to what I said, the two communities work independently of each other. We don't even know that this is how the other part of the equation works. And without folding all of that in, it's going to be difficult to make solid scientific progress.
I was intrigued in this way because supernova we can't detect outside our galaxy, and it's something is coming from.
We detect supernova too.
No, in GW. Yeah, it was a BNS signal.
If it is a supernova, okay, if 80-20-25 ULZ is a supernova, it is completely unrelated to the gravitational wave event. Nobody is doubting that. Okay. In the past, there have been papers published by Lipunov, for example, claiming that a BBH signal came from a supernova 1A, and everyone laughed at him because we know that's not how it works, right? So we know that there is a transient there. The chance coincidence probability is non-negligible. I don't remember the number, but it is not 90% probability. It is like probably order of 10% or a few percent, right? So it can happen by chance. But the question is that the object itself, now you remove all the GW from the equation. We saw this transient and many telescopes were used to study it. Is it a supernova or is it a kilonova plus off-axis afterglow? We don't know. And unfortunately, we'll never know. That's the problem. If we see a dozen more such events and we realize, oh, kilonovae often come with off-axis afterglows, we'll say that, okay, this is more likely that this happened. And then if in the next 20 years we still find no event that looks like this, we'll say, okay, it was probably an odd supernova. That's it.
Okay, thanks.
Continuation of what he was asking. So if the second bump is from off-axis afterglow, what is the constraint on the X-ray emission and the radio? Is there any?
So we have deep Chandra and XMM observations. Those are coming out in a partner paper tomorrow. We are broadly, so in getting X-ray data, at 1 keV you have to worry about absorption and there are uncertainties there. But at 10 keV we are marginally consistent. So one of those upper limits within 3 sigma we are consistent with, rest of them we are consistent with. Radio is giving us a lot of problems. Radio, the off-axis afterglow model does not fit well, but all the typical off-axis models do a lot of simplifications in radio physics. For example, most of them don't include synchrotron self-absorption, or the models that we've been running are not including those in things like JetSymPy. And the other problem is that if you just look at classical GRB afterglow modeling, right, completely unrelated to gravitational waves at all, often enough radio data doesn't agree with the full model. So our models right now are inconsistent with some radio upper limits, but I'm not too worried about that because we've published or we have read a large number of papers from GRB stalwarts who say that X-ray, optical, everything else works, but radio we can't explain. So similar thing. So, some of these partner papers we have not yet read even. So I've been traveling so much that I haven't had time to sit and think. X-ray is dim, but as I said, within 3 sigma consistent with expectations from our off-axis afterglow. We have only upper limits. There's no X-ray detection.
Okay, let's switch gears a little bit and maybe move to the second bullet point in bold. So we don't have clarity on the formation of binary black holes. What will be necessary to reach consensus? Cole, did you have any ideas to, any answers to your own questions, any suggestions?
Yeah, I think it's going to be a challenge because the creativity of theorists is unlimited. But I think that some of the things that are beginning to emerge may help in the following sense. If we can get better, more densely sampled templates, which can involve truly generic mergers and coalescences involving eccentricities and spins and things like that. I think eccentricities in particular are promising for the determination of whether we need dynamical processes. I don't think that modeling is going to necessarily improve that much from the isolated binary community because there are just too many moving parts. But I do think that if we have a sense for the true eccentricity, and especially if we can detect smaller eccentricities that are definitely non-zero, I believe that will help. But I am really interested in what other people have to say about this.
A quick comment on that from my side. So I remember there was this one event, GW 190521, which was a binary black hole merger, for which there was a claimed EM counterpart. And the claim was that, you know, it merged in an AGN disk, and that resulted in the production of an EM counterpart. And they even predicted, so it was sort of like this projectile motion where the kick actually kicks out the merged binary out of the disk. And they predicted that after a few, I think, decades, it will again plunge into the disk, and again, you will have an EM counterpart. I don't know what is the current status of this association, but nevertheless, do you think this could be a potential way by which we could determine the environment of a binary black hole merger, if we get lucky? Yeah.
Yeah, I think getting lucky is getting incredibly lucky. I am very skeptical of that particular claimed association. One of the challenges, of course, is that if you're trying to get an EM counterpart from some black hole that's tens or 100 solar masses in an AGN disk, is that you're competing with the natural variability of a disk around a 10 to the 8 solar mass black hole, which can be much, much brighter. But yes, in principle, if there is a definite EM counterpart established somehow, then that is going to limit the environment a lot unless you're willing to go for really exotic physics, because you'd expect in almost all other circumstances that stellar mass, tens of solar mass black holes are not going to have enough matter around in order to light up. So the AGN disk possibility would be great, but you'd probably want to look for things like radio emission, because the only way that I could suppose you might get something that could compete with an AGN is if you're lucky and there's a jet which is pointed directly at you. So I think you want to look for radio emission. But I agree, that's an interesting route to pursue.
Otto, you had a hand up. Did you want to make a comment?
Yeah, well, maybe it's more really of a follow-up question to that. I know that for specifically these AGN channels, there has also been suggestions, including from some of our colleagues, to look for lensing signatures from the AGN, and that's certainly a possibility also for looking for kind of these additional signatures on top of the flares. But one of my broader questions, maybe this is for Aditya and Saurav and Cole, is are there sort of these predictions for the various formation channels that people have been thinking about to sort of look for additional signatures beyond the gravitational wave signatures to try to verify or make predictions for the various formation channels that you could verify either in the EM or with sort of well, in other channels or with other methods.
I can talk a little bit.
Oh, you didn't? Okay. Okay, yeah, please go ahead. Please go ahead. Yeah.
Yes, I'm sorry to interrupt. I think that there is a bit of a case, if you recall the very first announced detections, 1509-14, there was a gamma ray signal, which was seen with Fermi, and the claim is that there was an association. I think most people now believe that this was possibly a short gamma ray burst, but it was unassociated. Nonetheless, at the time, there were quite a few papers that came out making suggestions of exotic nature about how you could get an EM signal. I think that on examination, it would be very difficult to get any of those. With that in mind, I think going back to the previous point that was raised, if you really have a definite EM signal, it's difficult for me, at least, to understand how this could happen in an isolated binary environment, unless you get super lucky with a third star somehow, or a dynamical environment. So I think that really would point to an AGN origin. Another thing in terms of an EM counterpart that has been pointed out is that eventually, if the population statistics get good enough, people have already started trying to do correlations of the very large uncertainty regions of the individual detections with AGN. So particularly when LIGO India comes online and we reduce the uncertainty by an order of magnitude or more, those sorts of associations, even without specific EM counterparts, hold promise, because if you are statistically significantly having error regions that include AGN more than you would expect, then that is a pretty good hint without anything else going on.
Just to comment on that, what I believe happens with multi-messenger between GW and EM is that when a lot of these telescope groups see that the P astro for BBH is very high, they just don't point in that direction, right? I mean, that's my it's not true. That was my understanding.
There are so two things. One is actually this was what I raised my hand for, that the AGN question is, in my opinion, more likely to get answered statistically, saying rather than on an individual event basis, saying that in general, exactly what he just said. But then there are dedicated programs that are there for BBH counterparts. For example, there's a group, one of our collaborators runs a program on DECAM, where they trigger on high significance well localized BBH sources and go quite deep to see if there are counterparts.
I see.
The other part though is that surveys like both the LSST and ZTF are scanning the sky whether LIGO is running or not. So you can go back, just as if I give you a trigger information later, you can go back in GW data. There's larger and larger volumes of synoptic time EM data that's becoming available, where you could go back and look at it to do some of these searches. It just needs people to be asking these questions, assigning them to students as projects, do a simulation paper. Is this something that might give a result? So if these guys, for example, come up with a model which says that, okay, maybe 30% of black holes are going to be in AGN disks, and then you fold it through how many of them will give you emissions. And then there are tools that are available that will allow you to simulate a universe with those parameters, saying that, will we see AGN flares? And you could then match them against data that's already out there. So this is doable today, if only someone is asking this question and then seeing it through.
Oh, well, it's good to know that people are following up BBH mergers. Then that's great. Saurav, I think I probably hijacked your question, or I
Yeah,
went
so
before you.
we have moved quite far from what Cole first mentioned, but a few thoughts about AGN and non-AGN. So eccentricities are going to tell us a lot about it. Johan Samsing, I think 2020 or 21, had a really nice paper. So if you find eccentricities at high frequencies, and it usually indicates that it was active Kozai-Lidov, and if it is in AGN disk, then the inclination distribution of the eccentric mergers was very different from the expected inclination distribution of eccentric mergers coming from clusters. And the reason behind this is, since the black holes that will do Kozai-Lidov with the supermassive black hole in the AGN disk, they tend to be aligned with the disk itself. There is no, there is a loss of isotropy just because of the geometry of the problem. So I think that's a really nice thing to look for.
I'm not sure, because different AGN disks would have different orientations, right? You're not expecting to have multiple mergers in the same AGN disk.
No, population level.
Different AGN disks could have different inclination with respect to us.
I will have to remind myself what it was. No, so I think, so this was the chi effective, not the inclination of the observation. The chi effective measurement. So that had a different signature in AGN versus non-AGN.
Right.
For eccentric mergers.
One other thing to note, though, that is, if you're trying to rely on the Kozai-Lidov effect, if the binary stellar mass black hole in the disk is in the same plane as the supermassive black hole, that's not a good configuration for Kozai-Lidov. So there could be other ways of generating eccentricity, but that would probably not be it in that configuration.
Yeah, agreed. So anyway, that was Samsing's paper. But even more importantly, I think the biggest uncertainty that has been plaguing since the beginning of all this modeling and so on is, there are too many knobs in the isolated evolution channels. And none of these knobs are very easily fixable or falsified using observations directly. So one way to advance, I think this has been known for a very long time, it just hasn't been done in a systematic way because it's just too much work. So for example, if you want to tweak the alpha or lambda parameter to match the rate or property distribution of gravitational waves, then you should also look for what is the effect on CVs, LMXBs, and like all kinds of, kinds of sources that has an active binary progenitor, right? similar to nettle kicks. If you want to match the gravitational wave observation by way of reducing the black hole kicks, mass dependent or mass independent, whatever, it doesn't matter, you have to go and check, okay, so I also see these detached binary black hole systems in Gaia, I also see these LMXBs, I also see these kind of other black hole sources. Do they consistently match the whole population? That hasn't been done, partially because it's too much work. The other type of data cannot be downloaded as a table. It's just hard. On the dynamic side of things, there are much fewer knobs. Dynamics just takes over and do its thing. But the one big uncertainty is cluster formation times. Because what we are very certain about is once a cluster forms and forms all these sources, what's the delay time? That is very well understood. But how to connect that to redshift is not so much so, just because what that t equals 0 means in terms of redshift, that's where the uncertainty is. I'm hopeful that with JWST observations and more detailed cosmological simulations and, like, for example, universe machine modeling of how to connect dark matter halos to galaxies and so on, I'm hoping that those modelings and uncertainties will improve. But yeah, these are the kinds of uncertainties that we have to be careful about.
If I could follow up on that, I agree with you that trying to understand the whole population, this is really the only way to go to constrain some of these many knobs, as you put it. There was an earlier talking about the possibility of using Gaia. There have been some claims of 30 solar mass black holes and so on. But there is a rather major issue, which is that we see so few black holes in our galaxy. From stellar evolution theory, we would expect maybe 100 million, 1 out of every 2,000 stars. And we have pretty good evidence for about 30. So this is something where we have to be absolutely on our guard against selection effects. In principle, if we can include all of that and forward model, as people have emphasized, that'll be helpful. But it, as you noted, is not going to be an easy task.
I'm really hopeful about Gaia. So it really feels like there will be hundreds of these black holes in the Milky Way. Of course, Gaia can only do Milky Way and very close by. We'll see.
Agreed. And in principle, if microlensing can give us more information, every bit of information helps.
I was just going to say we're 15 minutes past the hour. So maybe Sanjit, last comment.
Very quick comment about the AGN. Maybe it assumes that the AGN is localized. Then you can check whether the black hole spin is aligned.
Perhaps. I actually have forgotten the details of the Samsung paper. I just remember. Yeah.
Quickly say, this is about chi-effective and trying to see if the spins are aligned, because I think there was some mechanism by which the spins of the two black holes, the smaller black holes, are aligned. So. No. Just the thing that we see in LVK has aligned spins.
Of the individual black holes, alignment of that with the orbital angular momentum. That's what.
You're also right. But in the AGN case, that can get aligned with the disk.
No. Okay. So several things. You need to have Kozai-Lidov so that it becomes eccentric. Then of these, the distribution of chi-effective has a very specific signature if it is unconstrained Kozai-Lidov. In case of AGNs, what they find, I do not remember the details, is that the chi-effective distribution is very different from this unrestricted Kozai-Lidov chi-effective distribution. Because the black holes, the stellar black holes binary is residing in the AGN disk. So as a result, it has some restrictions of angles or spins or alignments and so on. I do not remember the details.
Very, very exciting and interesting discussions, but perhaps we could continue discussing over coffee. There are a few more days, and I just wanted to thank all the panelists and all the speakers for their time and their thoughts. Thank you very much.